The following program is brought to you by Caltech.
The final presentation before our break is Bethany Ehlmann. She's an assistant professor of planetary science, and she's also got a joint appointment with the Jet Propulsion Laboratory. And the topic of her talk is the future of Mars exploration.
Okay, great. Thank you, Ken. Yeah, I was asked to speak mostly about what is to come, but in order to understand what's to come, I think it is important to understand a little bit about the history of what it is kind of in a broader sense that we're looking for in order to understand what the big remaining questions are. So many of you who have listened to us talk before are perhaps familiar with this picture. So we've tilted Mars on its side. This is an elevation map. So we're looking at the northern plains of Mars. And you can see, of course, these large channels feeding the northern plains. It looks for all the world like there should have been an ocean there. But we don't see the chemical or the mineralogical evidence that would suggest that there's an ocean. So the big question is, what was Mars in the past? What is it that carved these channels? What was water like? We're getting part of that story at Gale Crater, and the rest of it is recorded in other geologic sections scattered around the planet. So the history of Mars exploration up until about the 2000s looked a little bit like this. Everywhere you see gold, something good happened. The mission worked. Everywhere you see red, failure. So it was about half and half here, going through the 60s and 70s. I'm coming up to the enormous successes of the Viking missions in terms of landing twice in the northern mid-latitudes of Mars. Russia had a success in the 80s. There was a long period in between when NASA was not terribly active sending things to Mars, and Russia was not either. But then a string of successes in 1997 with the small Mars Pathfinder rover that John mentioned, as well as an orbiter. Also, and importantly for the Mars program in 1996, interest in Mars as a potential habitable place for life peaked with the discovery and the claims made about this meteorite in terms of finding these morphological potential biosignatures, some chemical evidence of organics, in particular minerals associated with life. I think you would find the consensus in the Mars community today that this is probably not at least the Grand Slam home run evidence for life on Mars. Nevertheless, it certainly piqued interest and curiosity about what the red planet had in store, and partially as a result of that, a whole series of missions sent to explore, both sent by NASA and by the European Space Agency, Spirit and Opportunity, and the Phoenix lander that landed near the poles. So stemming out of this sort of decade of discovery in these series of missions, there are a number of important findings. Some of the top 5 I've listed here, and I'm going to focus on just mention 3 of my favorites, because both of these have big, outstanding questions still associated with them. The finding that Mars may, even in the present day, still ephemerally host liquid water. Questions concerning whether or not Mars hosts a gas, methane, and then some of the evidence for ancient water-related environments that were potentially habitable beyond the Curiosity site. So let's go to the first one, though, here. This evidence for modern liquid water. So these were images that were snapped by the HiRISE camera. The publications was first in 2007, but they've since been tracking these now for 6.5 years. And what you see, so this is an equatorward-facing slope, and what you see is that when the temperatures start to creep up in late spring, well, then these tendrils start to creep down the slopes. Lots of people have scratched their heads, including the first author of this paper, who is not a proponent of wet Mars, to try to figure out what could be causing this that's not water. But to date, all evidence points to the fact that there is something, whether it is ice melt to form fresh waters, or maybe some minerals that are in the regolith that contain water in their structures deliquescing or releasing that chemically bound water, that is what is causing this slope darkening and this movement of that dark tendril down slope. It's a mystery, though. We don't have direct evidence of either of those two causes. So the other mystery is methane on Mars. So this had been reported by a few groups, I think most credibly by Michael Muma, based on telescopic data. And methane people are excited about because it's not stable. It has a dynamical, its lifetime in the atmosphere of Mars is less than hundreds of years. So if it's released, it should go away quite quickly. And Muma was observing plumes in different areas of the planet at different times that seemed to be created rather quickly. So this pointed to a few things. It was probably, in the amounts that he was seeing, it was probably too much for a cometary influx. So that pointed to a number of exciting possibilities. Maybe Mars is volcanically active, erupting out methane. Maybe Mars is hydrothermally active. Water circulating in the surface are producing gases from chemical reactions with the rock. Or the most extraordinary explanation could be that, like on Earth, there are some microbes that are methanogenic. That is, they produce methane in the process of their metabolism to create energy. Now, this is a puzzle, though, because MSL Curiosity, we have a gas chromatograph mass spectrometer that can ingest the atmosphere of Mars. And as of the first half Martian year, no evidence. So this is a puzzle. This is something that Curiosity is still searching for and will continue to do so throughout its mission. So pay attention to the methane space and see whether we indeed find any. So, and then the final of the discoveries that I think is most interesting, and this is the focus of my work. In fact, this picture is the first planetary mission that I was privileged to be a part of when I was an undergraduate. And this was in 2004, the landing of the Opportunity rover at Meridiani Planum, hit an interplanetary hole-in-one landing in small Eagle crater. And when driving up to the outcrop, you can see a lot of driving took place. Right, this is the story unraveled by John Grotzinger, Steve Squires, and others of ripple cross stratification indicating shallow playa lakes, mineralogy of hematite concretions and dissolved crystals indicating acid weathering, acid Mars. So that was the story from the rovers. Coming up, the story then switched to to the orbiters for a little while. So these orbiting missions, and here I'm showing the MRO spacecraft here with the CRISM spectrometer. So CRISM looks and images the surface, but when it takes an image, it takes it in 544 different wavelengths of light. And from this, you can build up a spectrum that has characteristic vibrational absorptions that are indicative of what the surface is made of. In this case, it's a smectite clay, a phyllosilicate structure with water in it. So we can go across the surface of Mars, looking at various places, correlating mineralogy with images, if I can play. And this is to show you, this image was put together upon the discovery of one of the mineral carbonate on Mars. So this takes us through to what the Viking imagery provided us from the 70s, through to what circa 1997 we were able to see on the surface. Then flying in still more, using the data from the 2005 NASA orbiter, you can see now that we're heading into this system where water-carved channels came down to these tectonic scarps, and the water's flowing down, swept away the material on the surface, eroding through to create a stratigraphy. And now this is CRISM data showing materials of different composition overlaid on high-rise. And the blues that you see here are clay minerals, and everywhere that you see a greenish hue is the stratigraphic layer of carbonate placed above the clay. So now I will say I was involved in this press release, and this image took about probably 20 man-hours or so to produce. It was a big deal, but it was actually the three-dimensional imagery in the background that was used to make this pretty press release image for the carbonate actually 1 year later led to a paper because it let us better understand the stratigraphy of these units. So this kind of rapid use of 3D data is something we're working on right now at Caltech, pipelining this process, getting it faster so we can use it for geology, and that's seeded partially with the funds that Foster Standbeck has contributed here to the division. So we're putting it to use to be able to do cool things like this in more places. So some of the other environments that we see, though, are not these ridges of clays that are maybe hydrothermal, but other places where you'd see sort of a top-down weathering. Like if you were to go dig a soil pit, you would see layers of clay overlying bedrock if you dug deeply enough. This is what we think we're seeing in other parts of the planet. And in still others, we see evidence for deep lakes, which led to deltas forming and flowing outward. So that's the last decade in 10 minutes. what does the future hold with these outstanding questions about where the habitats are, what's causing this present-day liquid water, is there methane or not? So, as John just talked about, we have the most capable in situ laboratory ever sent to the surface of another planet, with ability to measure isotopes in rocks, X-ray diffraction of mineralogy, shoot lasers at rocks and get chemistry. This is all new for planetary exploration. What the next few years hold are, in the first instance, for our next 3 years, we're going to be focusing on the atmosphere and on geophysics. So the first mission, and it's actually on the way now. It launched in November. It's called MAVEN. It's led by an alum of this program, Bruce Jakosky, PhD, 82, now professor at University of Colorado. This mission is focused on the question of, well, did Mars once have a thicker atmosphere? So it focuses on the composition of the upper atmosphere of Mars and measures those processes of loss of the atmosphere. So stay tuned to results from MAVEN. It arrives in September. Europe is planning to send an orbiter to study in greater detail the composition of the atmosphere, following up on the methane discoveries. But the next mission coming out of JPL is this mission here, InSight. It was actually not formally part of the Mars program. It was selected competitively among a suite of missions across the solar system. And it is going to measure some very fundamental aspects of how Mars works. It has a seismometer on board, so we will hopefully learn, are there Mars quakes? Is Mars tectonically active? Is there still volcanism or internal movement that causes, in effect, Mars quakes? The next is it will have a probe of heat flow, a fundamental property. How fast does this planet cool? How has its internal evolution affected it? And we do not know heat flow to at least a factor of 2, and this is very important for almost every single model of planetary evolution. And it also contains a station to continue our meteorologic record of temperature and pressure on the surface. But what I'll spend the remainder of the time talking about is the next rovers, and in particular, Europe has been planning on sending one, but I'm going to focus on the next NASA rover mission, Mars 2020, the charge of which is to explore a habitable environment, to help prepare for human exploration, as well as to cache samples. And as Ken mentioned, he's project scientist for this mission coming up. So this is Mars 2020, and it looks a lot like MSL, right? That's right. So Mars 2020 is based on the same fundamental technology and rovers, the same landing system. NASA has now developed the capability to land 1 ton safely on the surface of Mars. So let's use it to go somewhere else, to explore a different place, different environment, and for about $1 billion less, because we're reusing it and sticking on different scientific instruments. But what is unique and different, in particular, is the ability of this rover to cache. So this is a drill. It's a prototype drill. Might not be the exact same one that goes on Mars 2020. But the idea is that you drill into a rock, and as you go, you are not only doing excellent science in situ, like Curiosity, making measurements, but you're also filling this canister with these cores. And these cores are about the size of a piece of chalk. So as you go, as you drive, when you find an interesting rock, you don't just have to take your measurements there. You cache it. And with the idea that eventually another mission is going to come back and retrieve that cache, returning it to Earth for future study. So how do instruments get picked for these rovers? Well, it is a process. It is a competitive process. So the call went out. Science community, send us your instruments for Mars 2020. And there are a number of things this rover was tasked to do. And Caltech played a pretty large role in the leadership of some of these instruments. I led a proposal for a microimaging spectrometer to do fine-scale mineralogy and texture. Professor Joe Kirschvink in geobiology and geology worked with an alum, MIT professor Ben Weiss, to propose a magnetometer to measure whether Mars has magnetic fields as the rover traversed. There'd be a small boom heading out the back of the rover that would measure magnetic fields as it went. Ken Farley is involved in this, and Paul Asimov and others are involved in situ dating and chemistry that would get the chronology, as Ken talked about earlier, and I'll go into detail in a second, and then several proposed cameras for geologic context. So these are the ones that I'm going to talk about here. So the mission, the instrument that we proposed for the 2020 mission, this was myself, John Grotzinger, Woody Fisher, were involved in this. is to use that same technology that we used from orbit to discover clay minerals, sulfates, help direct rover landing sites to Gale Crater, to take that and miniaturize it, and then to apply that up into a rock surface. So this instrument would take a normal grayscale, very fine, 20 microns per pixel microimage of the surface, while at the same time acquiring, in this case, 328 wavelength channels, from which for every single pixel in the image, you can identify its mineralogy. In this case, various clay minerals, gypsum salts in this layer, and then areas with iron oxides associated, and you can map them out in fine detail with these gypsum crystals. So this would be cool. This is a capability that's never flown to Mars before. This was a challenge in miniaturization and occupied about 3 months of time in terms of figuring out, okay, so here's where it would go. It would go on the rover arm. So you drive up to the rock, deploy it, but the box that the instrument has to fit in is 13 centimeters by 13 centimeters. So this is how big the instrument has to be for it to be permitted to go. So it's a challenge in miniaturization, and you can see the relatively densely packed space that we fit it in here. But these are lamps protected by a cover that illuminate the surface. The light passes through a slit, through some mirrors, into a spectrometer, as well as the microimager, which you can't see because it's hidden behind all the rest of the infrastructure. But the mirrors direct the light to 2 places to create a microimage into the spectrometer to split the light to create the multi-wavelength image cube, and then with a number of cryo-coolers to keep us cool, and focal plane electronics to operate the instrument. So the name is Simba, and I thought I would just bring along a sample of the rocks that we were testing on here and pass them around. So the particular sample that's up there on the screen is this one right here, to get a sense of at what scale that you're looking at. So I'll pass that there. I'll just send these around, and you can see if you can determine the environmental history of this rock just by looking at it. I think this is where instruments like Simba are helpful, because what we're able to do with the imaging spectrometer technology is for every single pixel to identify what its principal minerals are here, in this case calcium carbonate, magnesium serpentine, pyroxene. But what we're able to do by looking at both the texture and the mineralogy together is really detail a story. So see if you can see this story as you get one of the rock samples that passes. So first, the dark clasts that you see form as igneous rocks with pyroxene. We see that in their spectra here. Then we see this other mineral, though, coming into varying degrees serpentine. It's a hydrothermal mineral. So that comes in, alters the clasts. Then you notice that these clasts are rounded, right? They're not fully angular. So you had something rounding them, water transporting them. And then the water evaporates, and these pink to white to blue materials in between the carbonate cements the whole thing together. So that's the environmental history of this site in one rock. Pretty cool. So the other huge, I think, instrument advance that would be enabled in part by the work here is to improve our ability to date planetary surfaces. So the present day state of the art looks something like this. This has more craters, so it's older. This has fewer craters, so it is younger. Now, there's a lot of people who spend a lot of time carefully doing this, but it requires some extrapolations. It requires extrapolating the lunar cratering record and studies of crater density, correlating that with the Apollo samples, scaling the amount of craters that the moon would receive versus what Mars would receive, and that's how you get these age numbers with their associated error bars. As Ken was mentioning, though, now the capability exists to do better, and Ken and Paul Asimov and a postdoc here, Julia Cartwright, as well as a number of people at JPL, were part of this proposal led out of NASA Goddard, with also some participation from NASA Glenn, to actually do this sort of age dating that we would do in the lab in situ. So the gist of how this process works, and I had nothing to do with figuring out the details, but is that you take a particular compound, lithium metaborate, that lowers the temperature that is required for the sample to be, for the potassium and argon to be completely released from the sample. You measure potassium vaporized from the flux as well as from argon. And then the nature of this is that the way you can do the measurement is that potassium-40 decays to argon-40. It's very difficult, though, to measure things in an absolute sense, to measure the absolute amount of argon-40 produced through time that one would want to make a date. But instead, this technique allows only the ratios to be measured, and that is something that is achievable with the present day of mass spectrometers, the sort of next generation on from the SAM instrument that's on the rover. Now, these are two cool things developed here. It's not certain they're going to Mars. It's a tough competition, right? So there are 58 proposals submitted for about 5 slots on the rover. So you don't want to be on this selection committee and have to review all the proposals, let me tell you. And you're constrained by cost. You're constrained by a number of factors that have nothing to do with scientific coolness or potential for new discovery. Nevertheless, I think what is important is that these efforts advance more broadly the ability, what is possible to do in situ exploration across the solar system. So looking ahead, I think Caltech has a number of opportunities. There's a lot of big data sets coming out of Mars. I alluded to that. And it requires some careful processing, integrating across data sets, but cross-training of geologists, geochemists with this instrumentation technique is, I think, a unique opportunity for this division right here to take advantage of in advancing planetary science. So I am nearing my allotted time, so I will just leave you then looking to the future and seeing how Caltech is stamped all over it. So thanks.